2.1b, the derivative and tangent line problem. So this is a continuation of the previous video. We're going to keep working with derivatives, but the long way, by doing the limit. Okay, so here is the official proper definition for a derivative of a function. Now notice this notation right here. This is f prime of x, and that means derivative. Okay. Now we're going to go ahead and use this version of the difference quotient, because that's what it's called. Difference quotient. Quotient means to divide. Difference means to subtract. That's what's happening. So there's subtraction and division happening here, right? It says the derivative of f at x is given by f prime of x equals the limit, and then the whole f of x plus delta x minus f of x divided by delta x as delta x approaches 0. And this is for all x which this limit exists, and f prime is a function of x. Okay, so we're going to go ahead and use that version. In the previous video I used h. I just thought h would be easier to swallow first time around rather than delta x. They're the same. It's just that I want you to be comfortable with both versions. So I'm going to use delta x for this example. It says find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 at the point 0, 1 and negative 1, 2. Okay, so we're going to find the derivative, or the slope, because that's what derivative basically means, at x equals 0 and x equals negative 1. Now, we're going to work with the function itself. We're going to work with the function first, get a general equation, and then when I'm done, doing the whole difference quotient thing, I can go ahead and plug in 0, get an answer, and then go back, plug in negative 1, and get an answer. It's better than doing this twice. You'll see what I mean. All right, so I'm going to write this out. So f prime of x, okay, that's the derivative. That's what we're finding. And we're doing the difference quotient. It is the limit as delta x approaches 0. And then, okay, so it's our function, but instead of x, we're using x plus a little something something. So it's x plus delta x. Okay, so remember, we're using x and f of x, and we're going to use our second point, which is x plus a little something, which in this case, instead of h, we're calling delta x, and then our f of x plus delta x. So these are our 2 points. Okay, so, oh, I forgot a parenthesis. So we're going to start off with y2, so f of x plus delta x, minus y1, which is this f of x, over our, oh my god, x2 minus x1. Now, if you recall from the previous example in the last video, it happened that at the bottom, the denominator, everything canceled out, and the only thing that was left was h. You could probably look back at your notes. Okay, I'm talking about example 3. Yeah. We had x plus h minus x. The x's canceled out, and we were just left with h. Okay, that's why we just have a delta x. And of course, it is part of the definition, right? Okay, so now I'm just going to actually use the function, the equation. So the limit as delta x approaches 0. All right, so our function originally was x squared plus 1. So this is our y2. But instead of just x, it's going to be x plus delta x. minus our y1, which is just f of x. So that's just the equation how it is. And then over delta x. We're going to have to distribute, FOIL, right? X plus delta x squared. I'm going to FOIL that out. And I'm going to end up with x squared plus 2 times x times delta x plus delta x squared. Okay, that is just foiling out this part. Let's see, x plus delta x times x plus delta x. And then you would just do x times x, that's where I got x squared from. And then x times delta x, that's just 1 x delta x. But then I do delta x times delta x, which is a delta x squared. And then I do delta x times another x, so that's the other delta, the x times delta x. So that's going to end up with 2. Alright, so that's just the beginning part. Minus, well, I'm not going to use the parentheses. Oops. Minus x squared minus 1, right? Because this negative gets distributed. Alright, then this is all on top of delta x. Cancel out the stuff that you can't. Usually you can, you should be able to. X squared goes away with the x squared. Okay, and then look around. There should be, oh, there should be something else, but I totally forgot to write it. So let's squeeze that baby in here. So x squared plus 2x delta x plus delta x squared, that's just this part. I totally forgot my plus 1 at the end. So plus 1, that's my bad. Alright, so now that plus 1 and this negative 1 cancels out. Sorry, didn't keep track of that one. Alright, so, okay. So what do I have left? I have 2x delta x plus delta x squared over delta x. Then I should be able to see that I have delta x's everywhere. I have one there, I have 2 of them being multiplied here, and 1 in the bottom. So then I'm going to factor out the delta x from the top. So now I have 2x plus just 1 delta x over delta x. And then that allows me to cancel out the denominator. And so now I just have 2x plus delta x. And as part of the limit, I get to plug in 0 for delta x. So 2x is my slope. Now this is a general form for my slope. So basically, this is an equation I can use to find the slope, and all you need to tell me is the point to plug into it. And they did tell us, right, at the very beginning, these x equals 0 and x equals negative 1, they wanted us to find the slopes of the tangent lines at these points. So now I can do that. So, okay, this is correct notation for derivative. F prime of x equals 2x. So now if I want to find the derivative at x equals 0, I'm going to plug in 0 and get 0. If I want to find the derivative at x equals negative 1, all I got to do is plug in negative 1 and I get negative 2. And here are my answers. And then this is a general equation for the slope. I can use this equation in general for any point to find the slope. These examples are really long. That's why there's only 2 more that I'm doing. Well, rather, from the last video. So we just did 1, and here's the second coming up. There's an alternate definition of the derivative, and this alternate definition is sometimes written as you see above here. F prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. Sometimes a is replaced with a c. So it might be f prime of c. And then so everywhere there's an a, just replace it with a c. But these are the 2 alternatives. They work exactly the same way. It's just they look a little different. Okay. So example 5, differentiate. So I have this equation, but I did notice I didn't include an x. So we're going to do this at x equals 0. So yeah. So we're going to go ahead and do this slightly different, but basically the same. So f prime of a equals, now it's f of x, minus f of a over x minus a. So we're going to treat the x as x and the a as a, even though they're the same, for the very beginning, and then later we're going to actually go ahead and replace all the a's with our x equals 0. So a is going to be 0. Okay. So f of x is the function, x cubed plus 2x, minus f of a. So that means our function, but instead of x cubed, it'll be a cubed, and instead of 2 times x, it'll be 2 times a. And then this above, x minus a. Okay, so now you might want to simplify some things, if there's anything to simplify. So x cubed plus 2x minus a cubed minus 2a over x minus a. So there's really not much I can simplify. So I think it's safe to go ahead and plug in our x equals 0, which is going to be a equals 0. And you know what I forgot? I forgot to write the limit. Oops. As x approaches a. Okay, so now we're going to go ahead and plug in 0 wherever there's an a. So x cubed plus 2x minus 0 minus 2 times 0 over x minus 0. So x cubed plus 2x over x. Ooh, they have an x in common, all three terms here, so we're going to go ahead and factor that out. So x squared plus 2 over x. The x's go bye-bye. So x squared plus 2 is our general form, I suppose. Yeah, general form. I could just go ahead and plug in what x was supposed to be, which was a, which a is technically 0. So, I mean, this one is good for when you have like a square root. Oops. So it's good for when you have a square root, but really, like, I think the delta x's are friendlier, because usually you just have an h on the bottom or a delta x on the bottom. Here you have like x minus something. It's more difficult to take out. You have to factor, usually, whatever. Well, there's the answer. Okay, next up. All right, no more difference quotient. Here we're just going to talk about differentiability. If a function is differentiable, then you can already say to yourself, oh, it is continuous. Okay, that's something that you need to know to answer some questions, because sometimes they won't tell you something's continuous, they'll just tell you it's differentiable. So then you have to be like, oh, well, if it's differentiable, then it's continuous. And that way you can answer some questions. But I do need to stress, a function can be continuous, but that doesn't mean it's differentiable. So just because a function is continuous doesn't mean it is differentiable. So now we'll talk about how f prime of a might fail to exist. So how may the derivative fail to exist? So the first picture is a picture of the classic old absolute value function. Absolute value function is a perfect way to show when the derivative does not exist, and that is here at x equals 0. In fact, we're going to observe x equals 0 for all four of these pictures. So we're observing x equals 0 because that's where the problem occurs. Oh boy, I wanted to fix that r and now it just looks really weird. Okay, so observe. Okay, so this is called a sharp turn. And whenever a sharp turn occurs on the graph, that is a location, a point, an x value where the derivative does not exist. So it fails to exist. That's how they say it. All right, the second picture is a cusp. Okay, a cusp at x equals 0 here. It is not differentiable at a cusp or a sharp turn. Now notice how both of these functions are continuous. Okay, continuity does not mean differentiability. Now, if it is differentiable, then yes, it is continuous. But just because it's continuous does not mean that it is differentiable. Okay, that's a one-way street. Third picture, this is the location right here at x equals 0 of a vertical tangent line. So back to algebra 1, vertical lines have what kind of slope? Undefined, right? So whenever you come across a graph of a function at which a point the slope is undefined, that is automatically not differentiable at that point. Okay? And it is because of a vertical tangent line. And also continuous, by the way, but continuity does not mean differentiability. All right, the last example is an example of a jump discontinuity. And the derivative is going to fail to exist at any discontinuity. Okay, any discontinuity at all. Because in order for it to be differentiable, it has to be continuous. But just because it is continuous does not mean that it's going to be differentiable. Okay, these three examples right here are continuous, but it's not. The limit is, or sorry, the derivative is not differentiable at x equals 0. Right. So, example 6. Determine where the following functions are not differentiable and why. So the first one, it is not differentiable here, right? Because of the jump discontinuity. So not differentiable, I'm just going to write this shorthand. Not differentiable at x equals 0 because of jump discontinuity. Okay, so this function is differentiable here, 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 but not here. Okay, that's how it works. Oh, trying to erase, hitting the wrong button. Okay. The next one. There's an infinite discontinuity at x equals -1. So not differentiable at x equals -1. Again, because of a discontinuity. Infinite discontinuity. Infinite discontinuity. All right, number 3, third picture here. At x equals 3 right here, this is a cusp. So not differentiable at x equals 3, and there's just a cusp. Now the cusps and sharp turns, the reason it's not differentiable is because the derivatives, like you can't get the same derivative at that point from the left and from the right. It's kind of like limits. It's like you have a different derivative, so therefore it just doesn't exist. Okay, and then the last one, this is a perfect example of when we have a vertical tangent. See here at x equals 0? The only tangent I can make for that point is going to be vertical. Straight line up and down. So undefined slope. So remember, derivative means slope, right? So derivative is the slope. So if the slope is undefined, so is the derivative. So not differentiable. Wow, I'm writing really sloppy. Not differentiable at x equals 0 because of vertical tangent. I do apologize for my handwriting. It's atrocious today. All right, last but not least, a graph of a function over a closed interval d is given at what domain points? Domain are the x values, okay, in case you don't remember. Does the function appear to be I, differentiable, or sorry, 2, continuous but not differentiable, or 3, neither continuous nor differentiable. So we're going to analyze these functions real quick. Okay, so part 1 is differentiable. So where is graph A differentiable? Well, I see it's continuous. I don't see any sharp turns or any cuts or any discontinuities or anywhere that there might be a vertical tangent. So for part 1, it is differentiable everywhere in its domain. And its domain is -2 to 3, right? From -2 all the way to 3. So that is where it is differentiable. Part 2, it wants to know where is it continuous but not differentiable. Well, we established that it's differentiable everywhere, so there's nowhere that it is continuous and not differentiable. And then part 3, um, it wants to know the place where it's neither continuous nor differentiable. See, for this one, there was no such place because it's differentiable and continuous everywhere. Right, B obviously is not going to be as nice, right? So where is it differentiable? Well, let's see. There's a sharp turn right here, so it's not going to be differentiable there. There's a discontinuity here, so it's not going to be differentiable there. And there's another discontinuity here, so it's not going to be differentiable there. So now I need to state where it is. Okay, so from -2 to -1, but not including -1, we are good. We're differentiable. In case you don't know, closed bracket means including. Um, Open bracket means not including, right? Okay, so -1 is a no-no. But from -1, just not including -1, all the way up to 3, or sorry, 0, but not including 0, it's differentiable, right? Because all along here we're good. It's up till we get to 0, x equals 0, that we have the problem. Okay, so then after 0, so now I'm over here somewhere. We're good, we're good, we're good. So after 0, just not including, we're good. And then we get to this hole, and that's a problem. The hole is located at 2, so I just have to like tell myself I can go up to 2 but not include 2. And then for the last part, after 2 we're good, and then we're good all the way till 3. So that's where it's differentiable. Part 2 is where is it continuous but not differentiable? Okay, so basically, what part of this graph is continuous and not differentiable? Well, I wouldn't include this because that's not continuous, that's a hole. I wouldn't include this because that is a jump discontinuity. So the only place that it was not differentiable, but it is continuous, that's left, is right here. So I'm going to say at x equals -1. That's the only place that the function is continuous, but it was not differentiable. Right, part 3. It says neither continuous nor differentiable. So what were the places that this function was not differentiable, but also not continuous? Well, it would be these two that I left out of part 2. So you would say at x equals 0 and x equals 2. And that's that. Okay, so now you do have practice problems, and they relate to both 2.1a and 2.1b.